All right, so, oh, yeah, it works. I think you guys are happy to be finally rid of this thing. I personally got a little bit tired of the homework from section 7.3, like enough already. But, what I tried to do in picking out homework for this course was, as I told you guys, I'm not an expert in number theory or anything. So I don't have the greatest sense of what the best problem is to assign you. But my naive approach has just been to pick out problems that's off of Stillwell, which looked like they were doable and they weren't soul crushing. And sometimes that means that the homework is boring. So that's the way you felt when you started. I think the next one is a little easier, it's a little more, I don't know, easier, maybe it's more boring, I'm not sure. It didn't look too hard to me. I said I'd send you guys an email about it, I haven't gotten to that yet, but I should sometime soon. When's the next homework due? What is it?
Next week, right?
Next Thursday?
Next Thursday, yeah.
You're learning about another.
So, this is lecture 16, which isn't really lecture 16, obviously, but I called it lecture 16 for reasons I don't entirely understand. And what we're talking about today, more to the point, is quadratic reciprocity. And so the first section or two in Stillwell, he motivates why it's interesting, all right? I'm going to skip that stuff. We've seen that before. You can read it. Sufficient to say that the claim of quadratic reciprocity is interesting, all right? It was conjectured by Euler around 1750 or so. I'm not sure exactly on that. There was a proof given by Legendre in 1785. This proof used something called arithmetic progression. It assumed something about these arithmetic progressions of primes. And so that's, at first glance, it doesn't seem like that big of a deal, but actually, if you really want to prove this result which Legendre was using, if you want to provide proof of that arithmetic progression thing, it's actually harder than quadratic reciprocity, so it's kind of bad form to prove that using that, so the first proof of this arithmetic progression thing, Stillwell says, was given by Dirichlet in about 1737 or something. So the proof by Legendre wasn't quite right, incomplete at least. The first complete proof, which maybe it had an error, I don't know. Anyway, Gauss gave something like 6 different proofs of this over, or I don't know how many proofs. He gave several different proofs. Maybe I'm thinking if I'm not through arithmetic, maybe if I'm not through algebra, but proof was by Gauss. And I think it said he proved it when he was 17 or 19, something like that. And then he published that proof, I guess, in 1801, in that huge work he had on all kinds of things. And this was, I don't know how to say the word, it's, maybe you guys can tell me. D-I-S-Q-S?
Discord.
I don't know, I'm probably misspelling it. Approximate spelling. This huge work of Gauss in 1801, right, which he published when he was about your age. Yeah. But then he'd already found another proof of quadratic reciprocity. Neither of those proofs we'll see today. In fact, I'm not sure I'm going to prove quadratic reciprocity for you guys. Not this week anyway, I don't think. What I'm going to do is I'm going to cover the first part of this chapter and show you how it works. I'm going to give you everything that you need for the proof, pretty much, except for the proof. And then maybe we'll come back to the proof later if we have energy. Because the proof of quadratic reciprocity is difficult. even in Stillwell, and he's taken a rather efficient approach. If you open any other book, I don't think you'll find the proof he has. You'll find different proofs. In fact, that's one of the interesting things about quadratic reciprocity. Every book you look at, you'll find a different proof. And I don't know. Spencer said none of them are terribly natural, and it's just it's quadratic reciprocity, just something kind of surprising, yet inevitable. All right, so let me tell you how Euler's conjecture was. To start with, Legendre did do useful things. He introduced his symbol, this P over Q. This is his symbol, and we'll talk about that today a lot. All right, so let me start by just stating it. Euler's conjecture. We'll start with that, and then I'll quickly transition to Legendre symbol. Euler's conjecture simply stated this: when P and Q are both in the 4z plus 3. In other words, they have the form 4n plus 3. Okay. Then let's see here. P is a square mod Q if and only if, get this, Q is not a square mod Q. Otherwise, P is a square mod Q if and only if Q is a square mod P. Excuse me. All right, so I think we're assuming that both P and Q are odd primes here. I'm not absolutely sure. Definitely it's true when P and Q are odd primes. Otherwise, yeah, definitely the first part, definitely a pair of odd primes of a particular sort. I think the otherwise basically puts P and Q either in 4z plus 1 or 1 in 4z plus 1 and the other one in 4z plus 3. Okay, that's, I mean, P and Q both in 4z plus 1 or either P in 4z plus 1 and Q is an element of 4z plus 3. I mean, without loss of generality, that pretty safe movement, that's it. So let's see here. Let me foolishly think if we can find an example. Let's see. Let's look for P and Q, both of the 4 and 4z plus 3. How about what would you? Let's see here. We call this case 1, case 2. Let's see if we can think of an example of case 1, just to see, just to try to make this a little bit less esoteric. Let's see, 4z plus 3 is what? It's like what? It's 3, 7, 11, what? 15, right? 19, 23, 27, 31, etc. So we need to try to pick one of these. Let's see here. Is a square mod Q. Usually my luck is bad on these sorts of things. Let's try to pick one of these P and see if we can. Any of these squares? No, not off the bat, huh?
15 and 11.
15 and 11. So which one do you want to make P? P equals 15. And let's try P equals 15 and Q equals to 11. So then P15 is congruent to what? 4 mod 11. And of course, 4 is equal to 2 squared, right? So that says that, what does that say? It says that 15 is a square mod 11. So if we believe Euler's conjecture, that implies that what? That implies that 11 is not congruent to a squared mod what? Mod 15 for all a. Let's see. No.
In your first, if only if is a square mod q, and q is not a square, your mod q.
Mod P, yes. Yeah, thank you, Daniel. That would be really weird. No, it's supposed to be P. That's the reciprocity, right? That's the weird thing about this whole thing is we're saying things about something modulo P. By if you say something about modulo P of Q, then you can turns out say something about Q, maybe about P modulo Q. I mean, so you notice the flip-flopping here. P mod Q and then Q mod P, that's the reciprocity. Which to me is weird. Now, how would you prove that there's no solution? I mean, it's a very important symbol over here, which was what? Not congruent, right? That's kind of the whole point. Now, how would you prove that 11 is not congruent to a squared mod 15? Now, before we had this conjecture, you would have had a bunch of cases to check. I mean, to me, that's sort of the brute force way. I would just start plugging in things and see what happens. I suppose there are more elegant ways to argue it, but
15 does not divide 11 minus a squared?
15 is, yeah, all right, good. But again, I have to, so 11 in my thing squared is congruent to 0, right? Yeah, that's, in other words, you can trade this for trying to show that 11 minus a squared does not divide 15. Yeah, that's true. Or, wait, excuse me, other way around. 15 does not divide 11 minus a squared. But anyway, let's not, I mean, that's not the point here. The point is that if we believe Euler, then we already know the answer is that yes, in fact, there's no congruence. There's no square that gets you back 11 mod 15. But as you can see, that's a non-trivial claim, right? I mean, and he's claiming this for like arbitrary pairs. It's pretty interesting. Let's see, maybe the other one's more fun. So if we look at 4z plus 1, so what would the 4z plus 1 look like? 4z plus 1, you got what? 1, 5, 9, we got what? 13, 17, so forth. So let's see here. And then, so let's pick one from there, one from here. So let's pick 11. Oh, it's a bad idea. I want it to be interesting. So let's pick 15. And let's see here. What? Can you think of anything that 15 would be a square in this list? Mod that. 1 gives me 14. That's not, doesn't look full. I'm looking for a very boring one where it's automatically square. Oh man, maybe I picked the wrong number. What I want, you guys, is
9 and 5.
9 and 5.
P is 9. 5. Q is 5.
Oh, okay. Well, we can do that. I'll take it. Not what I was asking for, but I'll take it. So let's try that out. Oh, 9 is a square. 9 is a square in the integers, so yeah, that's probably gonna work. Okay, so let's see here. P equals to 5, Q equals to 9. Now, obviously, let's see here. So let's start with 9. 9 is equal to 3 squared, right? Mod. Certainly that's true mod 5. Well, let's see here. What does that say mod 5? let's see, mod 5, this becomes what? 9 is congruent to 3 squared, right? Mod 5, I'm just, but I mean, I guess the more natural way to write that would be what? 9 is congruent to what? Mod 5 is congruent to 4, right? Which is congruent to 2 squared mod 5. So then, anyway, so there you go. So 9 is a square mod 5. Excuse me. The reason this happens is that 2 and 3 are inverses mod 5. Okay. Well, maybe that's not the reason. That surely can't be a coincidence, though. But okay. So anyway, let's see here. Let's think about 5 mod 9. 5 equals, apparently 5 is congruent to a squared mod 9 for some choice of a. If we believe Euler's conjecture, right, we're in case 2. One's a square if and only if the other one's also a square. Modulo of the dual mod 9 versus mod 5. Well, this is easier. We just got about 8 cases to check, right? It's not 1. 2 is out. 3 squared is what? 9. That's it. Oh wait. Oh yeah. 3 squared is 0. 4 squared is what? 16, which is 7. Yeah. 5 squared, 25. What's 25 mod 9? 7. Yeah. 6 squared. Oh, 0. 7 squared. 49. Right. Mod 9 is what? 4. Yeah. 8 squared. I hope it's 8. Otherwise, we're really confused. 64.
Okay, that's 7.
What's that?
Do we get 8?
That is something.
Do we get with 7?
What was 7? 7.
Yeah, that's only 4. Oh, yeah, sorry, I just saw a square.
Oh. 7 squared is 49. 49 mod. I think it's 4.
It's 1, 63 is 1. 64 is
8 squared is 1.
64 is congruent. Oh, 64 is 1. 1 is not congruent to 5 mod 9, though. Huh. We're out of numbers.
You defeated the conjecture.
Oh, no.
Well, why does A have to be between 1 and 9, or A, does it have to be between 1 and 9?
Well, if I'm figuring out if an equation mod 9 has solutions, it suffices to check one thing in each congruence class. And there's only 179 congruence with non-trivial representatives. Aha! Unless we've made a mistake, and I don't think we have, this does not have a solution. So, it would seem that we have not made the conjecture as carefully as we ought to. What should we insist about P and Q? For odd primes, apparently, right? Because what you guys, I mean, the fact that we picked 9 was nice because it gave us a square immediately, right? But I don't believe the conjecture applies unless P and Q are both odd primes. Okay.
What's define? Is that literally odd prime, or is there a different definition?
Literally odd primes, a prime number which is odd, yeah. So it's prime, which means it has no divisors except for itself and
But not in.
in 1, and
Oh, 9's not a prime.
or plus or minus itself, and plus or minus 1. And odd, of course, 2z plus 1. That means that 2z plus 1 can either be 4z plus 1, 4z plus 3. And that's all she wrote.
So, under that condition, could we change it to 17 and 13?
17 and 13 would be hopeful. Yeah, let's try that out. Okay. Let's try 17 and 13. We'll do that. Let's see here. So 13, is that, oh, let's start with 17. 17 is congruent to what? 4, right? Which is congruent to 2 squared mod 13, right? So 17 is a square mod 13. So if we believe Euler, and he's had a lot of success so far in this course, I think Oscar inside, then this implies that 13 is congruent to a squared for some a mod 17, right? So you can start trying stuff. Obviously 1, 2, 3, no good. 4 is 16, 16 is 3, no good. 5 is 25, 25 mod 17 is 8, no good. 6, 36. What is it?
8, 64.
Oh, 64? So,
Right?
oh yeah, 64 mod 17 is what? 4 times 17 is what? 68. So it's minus 4. Oh, 8's it. 8 is linear. So this is congruent to 8 squared. Because 8 squared, notice that 8 squared is congruent, of course, to, let's see, 8 mod 17 is what? Okay, fine, 64, which is congruent to, so 4 times 17 is what? It's 40 plus 28, 68, right? So 68, if I subtract 68, that's like adding 0, right? So that's minus 4, congruent to minus 4, which is congruent to what? You can add 17, right?
13.
13.
I
I mean, that's
I was
otherwise.
like, wait a minute.
So yeah, so 13 is in fact equal to, 13 is equal to 8 squared, congruent to 8 squared, not 17. Yeah. Are we good? All right, so So I really should have written that over here if I had a brain, but as you know, I don't. So it brings into play what is called Legendre symbol. So P over Q. This is not a fraction, although this notation has certain logical similarities to fractions, so it's not a bad notation. But this is not a fraction in parentheses. This is Legendre symbol, okay? And by definition, this is what it is. All right, here it is. It is 1, when what happens? It is 1, excuse me guys. Oh, sorry, my definition on the page. 1, if P is a square mod Q, and it's minus 1, if P is not a square. Mod Q. Again, this is Legendre symbol. All right, so it turns out something interesting, and so not so interesting that you really want me to write it out in detail on the board, but interesting enough you'd like to see me project it. So let's do that. So I have time to write out the stuff that's more interesting logically. I'd like to actually write out the proofs of a couple things later, so if I'm not careful, I'll end up eating my time up for that on this less interesting part. So let me just show you. This is posted in Blackboard, by the way. I actually did find time to scan it for a change. Come on. Do it. by the way, guys, so what I'm hoping, if I don't mess up today's lecture, which is debatable at this point, is that we'll have sometime to start covering the rings chapter before the test. And the rings chapter actually, in some sense, we've covered bits and pieces of it in specific examples before. It will actually serve as a sort of review of some of the material which is on your test. So it's unlike this chapter kind of, this is out there. I mean, I don't think this helps you much at all with test 2, right? This is kind of its own thing. I mean, it has had bearing on things we've done, right? But a little bit different. So, again, Legendre symbols up the top. Go back one page here. So here's the thing. You can actually write. Wrong mode. The knife is here. You can actually write the. So if you look at the Legendre symbol for P over Q and the Legendre symbol for Q over P, you can rewrite the conjecture of Euler, which I just covered up with the projector screen, the one I wrote earlier, right? The one we just looked at a case of, You can write that conjecture simply as this formula. That's sneaky. So -1 to the P minus 1 over 2 times Q minus 1 over 2. Now P and Q are odd primes, at least to start with, okay? So what's Q minus 1? Well, that's an even number, right? So these half fractions, in fact, are just integers. So that gives you hope, right? That definitely means it's going to be plus or minus 1. But if you chase down the cases, you'll see that, in fact, that really is just a formula for what we claimed with Euler's conjecture. And here's the details. If P and Q are both of the form 4n plus 3, if I just put in like 4n plus 3 kind of thing and 4n plus 3 kind of thing, you end up with 2's both places, right? The 4's cancel. You factor out of 2, factor out of 2, then 4's cancel. You're left with a product of odd numbers, which gives you -1 to an odd power, which is -1. That's case 1, right? On the other hand, if either one of them is of the form 4j plus 1, then you end up with a product of an even and an odd number in the exponent, which of course is even, because -1 to an even power is 1. So there's proof. It's not exciting, but that is just a formula. There's the Corey proof. There's the, that gives you a formula for Euler's conjecture, and so this case 2 is interesting though, because it says two things at once, right? In order to get this times this is 1, right? That either means that P is a square mod Q and Q is a square mod P, which means this is 1 and that's 1, so 1 times 1 is 1. Or it means P is not a square mod Q and Q is not a square mod P, which gives you -1 to -1 gives you 1. And so logically that was case 2. All right, so that's the story so far. We have Legendre symbol, and more than that though, we also have this Euler criterion. Euler's criterion says something else. It's even a little bit more interesting. It says that P is a square mod Q if P to the Q minus 1 over 2, if it's congruent, if this is congruent, rather, to P to the Q minus 1 over 2 mod Q. Now that's actually a formula for the Legendre symbol. That's something beyond what we've had so far. And then you also end up having this multiplicative property for the Legendre symbol. This is something we'd like to prove. All right. And then we also end up needing to extend the Legendre symbol to -1 and to 2, which were not odd primes, obviously. Well, we're looking at positive integer primes, right? When you throw in -1, that allows you to extend to the integers. When you throw in -1 and 2, then you can extend to the integers. And so we'll do that. And then finally, here's the real the real result, the thing I probably won't prove this week. Honest to goodness, this is finally quadratic. You're like, well, what is quadratic reciprocity? You just defined a symbol and told me a couple patterns, and gave me an example. What really is quadratic reciprocity? We finally have the notation that we can state quadratic reciprocity simply and concisely as the following. This is what quadratic reciprocity says. It says the product of, P is a square mod Q, and these Legendre symbols, the product of those is just equal to -1 to the P minus 1 over 2 times Q minus 1 over 2. And that will tell you, when you look at that formula, whether or not one is a square mod the other. And while it was difficult to figure that out, obviously this exponent is a lot easier to figure out, right, than looking at explicit congruence relations, right? Okay, so, but there's another thing that you should notice, which is that because we're working mod Q to understand this question, you can replace P with its remainder. So one of the things we're going to be able to do is just to replace P with its remainder, mod Q, and then we would still have the same Legendre symbol. So let me put an example before I even give you any proofs. Again, here's a, in fact, it's the only real example he has in the whole chapter. I found a couple more in a couple other books, so I'll share those with you. Am I charging? Sure. Good. So here's how you actually calculate with Legendre symbol. And so here's the fundamental question will be what? Is 37 a square mod 59? That would be a real pain to figure out case by case, right? Like there's a lot of things to check. But we can figure out using quadratic reciprocity. Here's how. So first of all, because 37 is in 4z plus 1, that automatically means that the quadratic reciprocity, basically we have P over Q times Q over P is equal to 1, which means that I have equality of Q over P and P over Q. So I can flip them and do 59 over 37. Because we're in case 2, the thing I covered up. That's first move. Second move, because we're working mod 37, 59 is congruent to 22 mod 37. So I can trade a 59 for 22. See that? Just like Euclidean algorithm, right? So then you can use multiplicativity, which is that 22 over 37 is 2 over 37 times 11 over 37. This is a property of the Legendre symbol proof, okay? And then by the supplement, because 37 is not congruent to 8n plus or minus 1, that means that 2 over 37 is equal to minus 1. That's something else we'll prove today if everything goes well. Maybe not. That gives you this, right? And then you can flip it over again because, let's see here, 37 is what? It's 4 times 9 plus 1, right? So we're in case 2 of reciprocity, which means that this is equal to it's flipped over. And then you can do the remainder again, right? So 37 mod 11 is 4. And then use multiplicativity again. That's 2 times 11, 2 over 11 to 2 11, which gives me that. And then I use supplement 2 again, which tells me what the reciprocity of 2 was mod 11. 11 is not of the form 8n plus or minus 1. That tells me that this is equal to minus 1. Minus 1 squared is just 1. And that gives me minus 1. Which then tells me that in fact, no, 37 is not a square mod 59. Without so much as checking one case. This is the dark magic of Euler. And I mean, how he saw this, I have no idea. I mean, I have some idea. We looked at the question of, is minus 1 a square? Is minus 2 a square? Is minus 3 a square? These things we looked at for x squared plus y squared, looking at the 2 squared theorem. We needed the Lagrange lemma ultimately rested on the case that m squared plus 1 was congruent to 0 for some m. In other words, well, no, m squared minus 1. Oh, curses. We had to have that m squared was congruent to minus 1 for some m in order to get that m squared plus 1 was divisible by the prime, right? If I remember right. So anyway, those arguments, those discussions, of course Euler had been through, right? And so it was those investigations which led him to this conjecture. That's what's described in the first few sections of this, but. All right, so that's where we're going. We need to prove some of these things. See if I got some examples here. I'm not going to do those. We did more interesting examples, right? So. Let's look at this one here. So, Euler's criterion. So I'll write the proof of this out. I know you guys prefer me to do that, so I will stop being lazy and get this away. Why is it in other disciplines it's considered good form to read from a black PowerPoint? Is that good in anything? I mean, it's good for me to do that when I'm making mistakes and when I want to be careful and, you know, but it's something we want to understand really the nuts and bolts of. We really need to write it out, kind of see how it's put together, right? Okay, so where did I put my notes? There. I think we can agree, though, this is weird, right? I mean, but interesting. Why should the mod Q world have anything to do with the mod P world? Like this, right? It's like quadratic reciprocity is like a wormhole or something, you know? So here's Euler's criterion. For an odd prime Q, P over Q, the Legendre symbol, is congruent to P to the Q minus 1 over 2 mod Q. Right? And hence what? Hence, P is a square mod Q, if and only if what? P to the Q minus 1, right? Over 2 is congruent to 1 mod Q. Let's see here, before I get carried away with the proof here, let me think back to the example we had earlier today. What did we just do? We did 13 and 7, was it?
17, 13, 17.
Yeah, we had P equals to 13, Q equals to, what was it? 17, right? And we saw that both of those were squares, right? Mod the other, right? Let's see, if we try on Euler's criterion here for, let's take it for a spin. 13 to the 17 minus 1 over 2. And we want to look at that. Is congruent to what? We're looking what mod? What are we doing here? Mod 17, right? So that's 13 to the what? 13 to the 8. Doesn't seem terribly hopeful that that's plus or minus 1, and yet it is automatically plus or minus 1. Let's see, that's congruent to what? Minus 4, right? To the 8, which is congruent to what? 16 to the what? To the 4, yeah. congruent to minus 1 to the 4, which is congruent to 1. Oh, good. What a relief. Whether was right. Okay. Would you like to summarize number theory in a sentence? Whether was right. Oh well. Okay, so we could go through the other one, but I won't. Here's the proof. So the proof is by a combination of Lagrange's maximum number of incongruent polynomial solutions. You remember that one we had, like an nth order polynomial congruence has at most n incongruent solutions mod prime. That was that put yourself in the Wayback Machine. It was like the first couple weeks. And the other theorem we use is the what do you call it? Oh, what's that thing? Fermat's little theorem. So let's do case 1. Excuse me. Case 1 would be what? Suppose P is in fact congruent to some square A mod Q. Okay. So hence, by definition of the Legendre symbol, P over Q is equal to 1, right? So we want to show then what? We want to show that P to the Q minus 1 over 2 is also 1. Okay? So consider then, P to the Q minus 1 over 2 is congruent to what? Well, we can trade our P for the square, right? So this is P to the, this is A squared to the Q minus 1 over 2, all right? Working mod Q. The 2's cancel, right? And so what we have here is this is congruent to A to the Q minus 1, right? But, I mean, we could go different ways here, but I'm just going to remind you that Q is an odd prime, right? So, in fact, what you have there is A to the Euler-Phi function of Q, right? The number of relatively prime integers less than Q is Q minus 1, right? How many relatively prime integers are there to 5? 1, 2, 3, and 4, right? Q minus 1. So that's Euler-Phi function of Q. And then Fermat's little theorem said that this was congruent to what? 1, right? Mod Q. So this is by Fermat's little theorem, which you have used recently to solve one of those nostalgia problems, right? At least I did.
Euler's theorem.
What's that?
Euler's theorem.
Euler's theorem?
Well, that's Fermat's.
Yeah.
It's Euler's.
Do you use Euler's theorem? Huh. I guess there's no rule that says you have to solve one way. So are we good? Then that proves it in case 1, right? Case 2 is what? Figure case 2 in a different color. So case 2 would be P is incongruent to A squared mod Q for all A of the integers, right? In which case what? P over Q, the Legendre symbol, is by definition minus 1. So we'd like to show the Euler's criterion is true. We would like to show that P to the Q minus 1 over 2 is in fact minus 1 in this case. So the argument is a little bit sneaky. I had to read it a few times before it finally hit me what he was saying. So I'm gonna use green here for this. Notice that if x is equal to p to the q minus 1 over 2, right? Then you might notice that x squared is equal to what? It's equal to, it's equal to p to the q minus 1, right? Which is congruent to 1 by Fermat's little theorem, right? Also, x congruent to 1 and x congruent to minus 1, you know, solve x squared congruent to 1 mod p. This was mod p, right? No, wait a minute. Not mod p, mod what? Mod q. So how many possible solutions are there? Lagrange's theorem on polynomial congruences says you can have at most 2 incongruent solutions to this mod of prime, because this is a second order polynomial, so you got at most 2 incongruent solutions. But hey, here are those 2 incongruent solutions. That's all that's out there. This can only be plus or minus 1. So despite the kind of like, we were looking at what, 13 to the 8th power mod, whatever, a second ago. And like, I personally think at face value, it looks like that might not work out to plus or minus 1, but this little argument here shows you that it is an inevitability. It is inevitable that it will be plus or minus 1, which is interesting. So what do we gotta show? We gotta show that the one solution is not allowed, and that it has to be the minus 1 solution in this case, right? That's what we gotta show. So you can also look at another polynomial equation. Okay, so the other polynomial equation I can look at is this one. But p to the q minus 1 over 2 congruent to 1, you could think of this as, you know, you could think of this as let's say, y to the q minus 1 over 2 congruent to 1, right? That's a mod q, right? That's also a polynomial equation. Q is odd, right? So that's actually an integer power. And that can have at most how many incongruent solutions? It has at most q minus 1 over 2 incongruent solutions. Again, because this is, you know, think of it as y, or if you like, think of it as x to the q minus 1 over 2. That's a polynomial. I mean, when you rewrite the minus 1 on the other side, think of it as f of x equals to x to the q minus 1 over 2 minus 1. Well, that can have at most q minus 1 over 2 incongruent solutions. So what we do now is I argue that I can give you q minus 1 over 2 of those solutions, which give you 1. And here they are. So notice y equals to 1 squared, 2 squared, 3 squared, all the way out to q minus 1 over 2 squared. These are solutions, right? As, you know, like solutions of y to the q minus 1 over 2, right? Why is that?
Because you end up getting like 1 to the Q minus 1 or 2 minus 1. Which by Fermat's little theorem is 1.
Right. Again, by Fermat's little theorem. So what? So therefore, P to the Q minus 1 over 2
Those are the only solutions, right?
is not, what's that?
Those are the only solutions.
Those, yeah, exactly, those have to be the only solutions.
And then there are primes.
Well, these have, the only solutions to this equal to 1 are squares. So, well, which is a prime? Yeah, P is a prime. Well, no, I don't think I said P was a prime here. No, P doesn't need to be a prime for this argument. So P to the Q minus 1 over 2 is not congruent to 1, right? Not congruent to 1 for any P which is not a square, right? Mod Q, of course. Because if it was, that means that you would have another solution to the Q minus 1 over 2 order polynomial congruence that we just found Q minus 1 over 2 solutions for. But that's impossible, because we already have all the solutions we can to this equation. You can't have any more, which means that this must be not congruent to 1 if P is not a square. Right? So what does that mean then, going back to the green? That means we have to fall in the minus 1 case, which means, going back to the beginning, that if P is not a square, it must be that P to the Q minus 1 over 2 is congruent to minus 1, which is what we set out to prove. There is a small gap in my argument. There's at least one small gap in my argument. And that is, why is it that this list is actually incongruent by Q? I mean, for example, if Q was 11, this is 11 minus 1. 10 over 2 is 5. 5 squared is 25, right? So it's a slightly non-trivial claim to claim that these are, in fact, incongruent. That was needed. I just swept it under the rug. You believe me that those are incongruent. They look different. But that can be proved. I will let you read my proof. My proof is on page 8 of the notes. Okay? It's very similar to other arguments we made, like decision hall arguments we made, where we tried to prove a list was like distinct things. So if you have any questions about that, we can talk about it another day. Now, with Euler's criterion, we can prove interesting stuff with almost no effort. this little result is really huge. I'm going to erase the proof before you can ask me more questions about it. So the multiplicative property. Let's prove that multiplicative property, right? So here was the theorem. For any P1, P2, incongruent to 0 mod Q, we have that P1 over Q, Legendre symbol, P2 over Q, Legendre symbol. By the way, this is also called the quadratic character of P with respect to Q or something like that. I don't know. Name calling aside, there's the theorem. How do you prove it? This is something you would like to be held responsible for on the next test. Like, given Euler's criterion, prove multiplicativity of the Legendre symbol. This is a question that you would like to have on your test. Here's the proof. So, P1 over Q. By the way, did you notice, one of the things you should notice from that last proof is that we didn't actually need Q with prime. And I haven't assumed that here. P1 and P2 can be whatever. Just being congruent to 0. Not multiples of Q. Multiples of Q are out. So P1, this is equal to congruent to here by Euler's criterion. Yeah, P1 to the Q minus 1 over 2 times P2 to the Q minus 1 over 2. Which by the algebra of congruences is congruent to P1 times P2 to the Q minus 1 over 2. Which by Euler's criterion, and one more time. Oh man. That's Euler. This is a sneaky one. Although, you gotta give it to Legendre, he's the one who came up with this notation, which makes it even more obvious, the structure, right? Explaining these things in the language we started with today would be daunting. It's this Legendre symbol that allows us to explain it so clearly. So you see why I say that that's a nice test question. All right, so that's it. Now, there were two supplements, all right? There were two supplements to this that you need to know in order to actually do calculations like the example we did today. You need to know the value of minus 1 over Q, and that's equal to 1 or minus 1. It's equal to 1 if Q is equal to 4n plus 1, and it's equal to minus 1 if Q is equal to 4n plus 3. And there's also the supplement by 2. 2Q, turns out, is equal to, oh, come on, where'd you go? Oh, there it is. Minus 1 to the Q minus 1 over 4 mod Q, or it's equal to minus 1 to the Q plus 1 over 4 mod Q. And the first case is for Q equal to 4n plus 1. And the second case is for Q equal to 4n plus 3. Now, here, it is assumed that Q is an odd prime. Okay. But you see, now that we have Euler's criterion, we can try to prove these things. Got the multiplicative property. So now we're back into the case where I could write these things out, but you'd really rather that I project them, trust me. Let me show you why. The proof that we're about to go through is asked me to bring back the Liberty newspaper. Daniel apparently wants to make a newspaper hat, so seems like good enough use for the school newspaper. Probably one of its better uses. Oh, I'm sorry, I'm kidding. It's okay. You know, you can't email the newspaper a letter. What is this? Like 1995? I mean, why can't you email the school newspaper like an editorial letter? You have to take it in person and sign a form? Really? Have you noticed that? Oh, I'm sorry. No, I'm assuming you read the school newspaper. How many here have actually read the school newspaper? Curious. Oh wow.
I've read
I mean,
random things.
Yeah.
But you have read it at
I
some
have,
point.
yes.
Yeah.
Okay, there's one.
I've read it.
I've glanced at it, I haven't read it.
Yeah, it's
through.
not like.
They haven't actually read it before, instead
I
of-
saw the picture.
Okay, I've got about a 50%.
I saw the one where Jerry lost weight, but that was about it.
Once or twice I got so bored that I've actually read it.
That was even food.
Did you enjoy it?
Not really. I mean, I don't know. I don't really do newspapers. All right, so, oh, here's the proof of that. This one I probably could have written this one out. Oh, sorry, it's too late. The value of minus the supplement, the -1/2. You prove by Euler's criterion. Two cases, right? If Q is equal to 4n plus 1, then by Euler's criterion, this is equal to -1 to the 4n plus 1 minus 1/2, but that's -1 to 2n, which is 1. And if Q is 4n plus 3, Euler's criterion, so -1 to the 4n plus 3 minus 1, which is 4n plus 2/2, which is 2n plus 1, but -1 to another power is -1. This would also be a friendly test question, yes? Less friendly would be to ask you to prove this. It would also be quite a drag for me to grade that. It's not that hard, really. The proof I'm showing you here is it's actually pretty much the same thing we did for Wilson's theorem. Remember Wilson's theorem where we took this string of integers and then you used the modulus to add things until you finally found other factors. I mean, the game that's played here is much like Wilson's theorem. Here it is. So, and this proof is somewhat nonlinear. Like, you look at what we're supposed to prove, right? And I don't quite see why you should look at 1 times 2 times 3 times times 4n. So the starting point for this proof is a little bit like, I mean, okay, you're looking at Q equals 4n plus 1. I guess it makes sense to investigate 4n. But you should notice that's kind of a sneaky step, the starting point. And then what does he do? So we're working mod 4n plus 1. So first of all, write 1 times 2 times 3 times 4 all the way up to 4n. He rewrites it as a product of the odd numbers times the even numbers. All right? Sneaky step number 1. Not so, slightly sneaky step number 2. Factors out of 2 from each one of these. Chunk, 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 chunk. You get 2 out of them. So you get 2 to the 2n. Okay, fine, whatever. Then, next step, he breaks the odd product into the first 2n minus 1 of them, and then the rest of them. Okay, that's slightly sneaky. That's pretty sneaky. I mean, why would you do that? I don't know. We do it though. So then, and then he's like, okay, now he's going to use the congruence. See, 4n plus 1 is congruent to 0, right? So I can trade, basically, I can trade this. I can subtract 4n plus 1 from that, right? And I'm trying to think how I got to this. Let's see here, 2n plus 1. Look what I've become. Almost, excuse me. I was scrambling the word, I think. 2n minus 1. is congruent to 2n minus 1 minus what? Minus 4n plus 1 mod q, right? But see what happens here? You get what do you get? Minus 2n, right? What's this? What's that? Yeah. Maybe. It's not right.
Just plug them all in minus 1.
But it's not the right pattern. Oh.
And you pull, and then that line you just pulled out a minus 1 for right?
Oh, you're right. Yeah, I'm sorry. Good one. This, yeah, you're right. This one was just pulling out a minus 1 n times. Oh, okay. Next one I use the congruence. Thank you. Yeah, so minus 1 is congruent to, oops, duh. No wonder I'm confused. All right, so minus 1 is congruent to 4n, right? Mod 4n plus 1. Right, thank you. And then this gives you the 4n minus 2 and so forth all the way to that, right? But then you look at it, what you got? You got these numbers here, and then over here you've got these guys. So then you start looking at it, you've actually, and then you got those. So you start counting, you got 1, 2, then 2n plus 1, 2n plus 3 all the way there. And then you've got, right, 2n plus 2 and these ones. So altogether you've got all the way from 1 to 4n, and then this factor out here. But that's what we started with, right? Consequently, this thing has to be 1. But, excuse me. And then how did I get to, oh, this is what, n is what? N is equal to q minus 1 over 4. And so that gives you this is equal to that. But then you can solve for the 2 to the q minus 1 over 2, and you get what? Minus 1 to the q minus 1 over 4. But by Euler's criterion, that is 2 over q. Es bueno. I mean, it is what it is. Now, there's two cases, right? We did the 4n plus 1 case. It remains to do the 4n plus 3 case. That may have defaulted you in the homework. I don't remember. I feel like the decent thing to do would be to remove that from the homework if it's there. But then again, it might not be that hard. I mean, do you think you could do it for the other case? I think I could. I bet it's about the same difficulty. We'll see. So you can take this case though, and you can collapse it down further. When I used when I used the 2 over q in the initial calculation earlier for the 37 and the 59, I did not use it like this. I looked at 8n plus or minus 1. It turns out if you look at these two cases and you put them together, if you have the first case, you can work out that basically the q is equal to 8m plus 5. On the other hand, if you have 4n plus 3, you can work out that you have 8m plus 7. And so if you look at this for a bit, you can kind of put it all together, put these two cases together, and you can just say this: 2 is a square mod q, if and only if q is equal to 8m plus or minus 1. So for example, if I have like 2 over 19, or if I have 2 over 7, 17, 2 over 15. Oh, well, Q here is not a prime, that's probably bad. I don't know. 23? Thank you. Yeah, sure. So this would be equal to what? This would be equal to what? This would be equal to what? So 8n plus or minus 1 gives you things like what? It gives you 16 plus or minus 1. It gives you, of course, 8 plus or minus 1, etc. 24 plus or minus 1. So these numbers would be like what? 15, 17, 9, 7, 25, 23, etc. Those kind of numbers. So let's see here. That is in this list, right? So that means that this is 1. This 2 is a square, mod 23. (17) is, in fact, of the form 8n plus 1, or minus 1, right? So this is 1. 19 is not of the form 8n plus 1. This is an 8. This is an 8z plus 3, right? Actually, that is, right, 19's in there. So this is equal to minus 1. In other words, 2 is not a square mod 19. Yeah.
Why is it 8 plus minus 1?
So we worked out that 2, the quadratic character of 2 with respect to q, is equal to minus 1, q minus 1 over 4, if q is an odd prime of the form 4n plus 1. Your homework maybe works out the other case. It turns out if you put these two cases together, you can summarize them in terms of this one overreaching criteria, that 2 is a square mod q, infinitely of q is of the form 8n plus or minus 1 for some integer m. I don't think it's altogether immediately obvious, but the arguments on this page show you, and they're not especially interesting. They're just kind of chasing down case by case. So guys, I have a few more examples I'll show you, but that's pretty much all I got for you on quadratic reciprocity for now. What's past this point in the chapter is a discussion of Chinese remainder theorem. If you're like me, you're like, what? So yes, he then talks about Chinese remainder theorem for 2 sections, and then that goes into the proof of quadratic reciprocity. So I may come back to the Chinese remainder thing later, if time allows, and I think it's healthy for the course, okay? But that's all I have for quadratic reciprocity. Next time I'll start the rings, which should be kind of in some circuitous way a review for your test too.